Okay, now we're going to be talking about the quantum circuit model. So here's the plan. We're going to build up to quantum circuits slowly. We're going to start out with the classical case, talk about the most standard kind of classical circuits that are made of AND or NOT gates. Then we're going to talk about classical reversible circuits. We're going to add some randomization to those. And finally, we're going to get to quantum circuits. Okay, so let's start out with the very standard case of classical circuits with AND, OR, and NOT gates. So here's an example. So AND and OR gates, they take two inputs and they have one output. A NOT gate just has one input and one output. Okay, so if you look at this circuit here, and let's just take an example. Let's say x1 is 1. So let's say we're in the case where x1 is 1 and x2 is 0. So this is 0 and this is 1. Okay, so this NOT here, this will evaluate to 1. And now my AND gate has two 1s coming in, so that it will evaluate to 1. This NOT gate will evaluate to 0. So now I have two 0s coming in. This will evaluate to 0. But it doesn't matter because I have an OR at the top, so because at least one 1 is coming in, this will evaluate to 1. Okay, so when x1 is 1 and x2 is 0, this circuit evaluates to 1, which agrees with what I have in this table here. Okay, so you can similarly compute the output of the circuit on any of the inputs here. Okay, so you might notice that this circuit is computing a familiar function. Right, it's just taking the XOR of the inputs. Okay, so there's two input bits, and the output is the XOR of those two input bits. Okay, good. So I'm going to make one change to this very standard kind of classical circuit. I'm just going to add another gate, which we're going to call the duplicate gate. So you saw that in the previous circuit, x1 was written multiple times. Okay, that's kind of annoying. So this is the same circuit where I just feed x1 into a duplicate gate, and that sends x1 both here and here. Okay, so this is just going to make our presentation more uniform with what comes later with quantum circuits. Okay. Yeah, so this operation is called fan out. So the value of x1 is fanning out to multiple gates here. Okay, so what Boolean functions can I compute with these circuits where I have AND, OR, NOT, and duplicate gates? Well, it actually turns out you can compute any Boolean function, okay? And that is fairly easy to see with something that's called disjunctive normal form. Okay, so what is a disjunctive normal form? What's the idea here? Well, the idea is that for any x in 0, 1 to the n, there is a clause, so that is just and of the literals of x that evaluates to 1 on x and only on x. Okay, so how does that work? Well, let's just look at an example. Let's say that x is the string 101. So this formula is going to evaluate to 1 on 101, right? Because x1 is 1, x2 is 0, so this NOT will evaluate to 1, and x3 is 1, so this is going to evaluate to 1. But any other string, this clause here, so this is just an AND of literals, that's what a clause is. This clause here is going to evaluate to 0, right? Because any other string is going to differ with 101 in some position, and on that, when I look at the literal corresponding to that position, it's going to evaluate to false instead of true. Okay, then since I have AND of everything, this whole clause is going to evaluate to false. Okay, so that gives us a simple way to represent any Boolean function. We can just represent it as the OR of all clauses corresponding to the strings on which f evaluates to 1. Okay? So that gives us a way to represent any Boolean function via and or not and duplicate gates. Let's just think for a second about how efficient this representation is. So every clause here is going to be of size n, right? Because there's n literals. And I potentially need up to 2 to the n many of them. Right? I need up to the number of strings on which f evaluates to 1. Okay, so the size of this representation is always at most n times 2 to the n. And that seems like it's really big, right? It seems like pretty wasteful. But in fact, it's not, because Shannon showed that even a random Boolean function actually requires at least a circuit of size at least 2 to the n over 3n many gates. Okay, so most Boolean functions require a circuit of this size. Okay, so this upper bound is actually not too far away from the best that you can do for an average Boolean function. Okay, so this is the kind of lower bound we can show for a random function. When it comes to explicit functions, we're very, very far away from that. So, even today, the best lower bound we have on an explicit function is something like size 3 times n. So just slightly larger than 3 times n. So very far away from what we can show for a random function. And usually we call a function efficient if it has a polynomial size circuit. So meaning that if it can be, if there's a circuit to compute the function that has size into the k for some constant k. Okay, so now let's take one step closer to quantum and talk about reversible circuits. So in a reversible circuit, every gate has to be invertible. So in particular, the number of inputs has to equal the number of outputs for every gate in your circuit. Of course, this isn't true, for AND and OR gates, right? Because they take 2 inputs and just have 1 output. So that means that, in an AND gate, just from the output, you cannot reconstruct the input. So you're losing information. And people actually started studying reversible circuits in the 60s and 70s in order to make real circuits more efficient. They thought that this loss of information would create excess heat in the circuit. The circuit would require more energy. So they were studying reversible circuits in an effort to make circuits more efficient. And so they developed a nice theory of reversible circuits, which leads very well into quantum circuits. Okay, so for reversible circuits, we can't use AND and OR, so we have to look for something else. And a very nice replacement is the Toffoli gate, also known as the controlled not gate. Okay, so I'm just talking about normal bits, but I'm kind of going to start using this suggestive notation of the quantum case here. But you should think of each of these as just representing 0 or 1. Okay, so the Toffoli gate has 3 inputs and 3 outputs, and if the first 2 bits are 1, then it negates the 3rd bit. Okay, and it leaves the first 2 bits unchanged. Okay, so if we look at where's an more interesting example over here. So in this case, the first 2 bits are 1, so we're going to flip the 3rd bit, so the 3rd bit becomes 1. Okay. So here's a nice way to write the output of the 3rd bit. So it just is C XORed with A times B. Okay, so if both A and B are 1, then this is going to be C plus 1, so we flip the value of C. So for reversible circuits, we also allow ourselves to be a bit more flexible. So we allow extra wires that can carry hard-coded bits, and we call these ancilla wires or ancilla bits. Okay, so using these ancilla bits, we can see that a Toffoli gate can simulate a NOT gate. Okay, so we just hard code 2 wires to be with the values 1. Okay, and now we can feed any bit into the third wire, and the output on the third wire will be the negation of that bit. Okay. So you see here that with ancilla bits also comes the notion of garbage bits. Okay, so for reversible circuits, we have no choice but that the number of inputs is going to be equal to the number of outputs. But of course, we might not be interested in all of those outputs, right? So we're going to designate some of the outputs as the ones that we're interested in, and the rest will just be garbage bits. Okay, so in this case, we don't care about what's on the first wire or the second wire. Our answer is just given by the third wire, in this case of computing the NOT. Okay. Okay, good. So now we can also see how we can compute an AND gate. Okay, so in that case, I again have an ancilla wire, this time on the third wire here, and I hard code the input to be 0. And in that case, the output is just going to be A and B. Okay, so again, using ancillas and hard-coded bits, with the Toffoli gate, we can compute the AND. We can simulate an AND gate. And since we already saw that you can also simulate a NOT gate, and now we can do an AND gate, you can use De Morgan's law to also simulate an OR gate. Okay, so there's just one more thing that we need to see in order to simulate all the gates from our classical circuit. That's how to simulate a duplicate gate. Okay, so that's pretty easy. So in this case, we have 2 ancilla wires. One is hard-coded to 1, one is hard-coded to 0. Here is our input A coming in on the first wire, and we take as our output, well, the first wire is unchanged, it just comes out A, and we get another copy of A on the third wire. Okay, so now we've duplicated A there on the third wire. Okay, so in these examples, you see that I've used ancilla bits set both to 0 and 1, but actually we can create bits hard-coded to 0 from ones that are set to 1 just by using our NOT gate like this. Okay, simulating a NOT gate with the Toffoli here. Okay, so therefore we can actually assume that all ancilla bits are initially set to 1, because if we need some set to 0, we can just create that ourselves. Okay, so now we come to the general form of a classical reversible circuit. Okay, let's say that we have N inputs, then we can have some ancilla wires. We can assume that they're all set to 1. Some of the outputs we designated as garbage, and some of the output wires here contain the actual output that we're interested in. Okay, so I actually took this picture from a lecture of Ryan O'Donnell, and I recommend that you check out that lecture as well. It's very good. Yeah, so this is like a scribe notes of his lecture here. Okay, good. So how do you interpret such a diagram? Okay, so you can always think of a diagram like this as just a list of instructions. Okay, so we just read it from left to right, and we see that the first thing that we're going to do is we're going to apply this Toffoli here, where the control bits are the first bit and the second bit, and the output, the target bit is the nth bit. Okay, so that's the first action that we're going to do. Then we do a TOEFL here, where the control bits are the second bit, and this first ancilla bit, and the target is here, the last ancilla bit. Okay, so then we do that, and we just keep going that way. Okay, so you can directly translate a diagram like this into a list of instructions. Okay, and that's often, for me, the best way to figure out what a circuit is doing. Okay, just to translate it into this list of instructions. Okay, so that's reversible circuits. Now let's take the next step and we'll go to randomized reversible circuits. Okay, so we're going to add randomization. Okay, so we're going to augment the circuit with another kind of gate, which is basically a coin toss gate. Okay, so it has no input and it just outputs 0 or 1 uniformly at random. Okay, and now we can always assume that all of these gates are used right at the beginning of the algorithm. Okay, so we just generate all our randomness that our circuit needs right at the very beginning. Okay, so now we're going to have basically 3 kinds of inputs. We're going to have our wires that are carrying the actual input, the data, then we're going to have ancilla wires, and then we're going to have these coin toss wires. Okay, so to get a feeling for how these coin toss gates work, let's analyze a simple example here. Okay, so we have this circuit. What is the output C of this circuit? Okay, so let's think about it in terms of the value of A. Okay, so let's first consider the case A equals 0. This case is easy because if A equals 0, then it doesn't matter what the outcome of the coin toss gate is, right? Because we're not going to activate the control here, so we're going to do nothing to the third wire. So if A is 0, then we know that C is going to be 0. 0. Okay, on the other hand, if A is 1, okay, then if the control is activated or not, depends solely on the output of the coin toss gate here. Okay, so in that case, with probability 1/2, the output here is going to be 0, in which case C will again be 0. And with probability 1/2, the output of the coin toss gate will be 1, in which case both controls are satisfied, so C is going to be 1. Okay, so you can see, you can kind of think about this as a controlled coin toss gate, right? So if A is 0, then we do nothing. We just leave C as 0, and leave the input of the third wire 0. But if A is 1, then the output of this third wire is going to be randomized. It's going to be 0 with probability 1/2 and 1 with probability 1/2. Okay, so it's like a controlled coin toss gate. Okay, so that's just summarized on this slide here. Okay, let's look at another example here. So what is the probability distribution over outputs in this circuit? So go ahead and pause the video, take a minute, and work this out for yourself. Okay, and I will continue with the answer here. Okay, so how should we think about this? Well, let's first look at, it looks like the most interesting case is if the output of both of these coin toss gates is 1. Okay, so let's think about this case first. And of course, that's going to happen with probability 1/4 that both of these coin toss gates evaluate to 1. So if this happens, then both of these controls are satisfied. So we're going to flip the 0 here. So that's going to become a 1. And then both of the controls are satisfied here. So that means I'm going to flip this bit here. So I get a 1 out here. Okay, so in this case, my output is going to be 1, 1, 1, 1. Okay, so that happens with probability 1/4. And now so the other cases, I don't think we'll get any of the TOEFLs to activate. The controls won't be satisfied. So let's look at one more example. Say I have a 0 here and a 1 here. Okay, so that case will also happen with probability 1/4. Okay, so in that case, of course, this just remains a 0, and then this is going to remain a 0. Okay, so then this stays a 0. So in that case, our output will be 0, 1, 0, 0. Okay, and with probability 1/4, so the second two registers shouldn't change if I flip this around. Okay, so let's make this 1, 0. Okay, then this is still 0, of course. Okay, so that's going to be 1, 0, 0, 0. And with probability of 1/4, if this is, oops, get the eraser. If this is 0, 0, okay, then yes, none of our TOEFLs are going to do anything. So our output's going to be 0, 0, 0, 0. Okay. Okay, so that's what happens. So that's going to be our output, right? With probability 1/4, we're going to get this. Probability 1/4, we're going to get this. Probability 1/4, we're going to get this. And probability 1/4, we're going to get this. Okay? So we can already, start to write this and maybe, so our output now, it's not going to be a deterministic thing. It's going to be a probability distribution over these 4 states. And we could kind of, suggestively, with the quantum case that's going to come, we could think about this as kind of this superposition, right? With probability 1/4, we're going to be in this state, probably 1/4 this state, probably 1/4 this state, or probably 1/4 this state. Okay, now we come to the quantum case. So the quantum case, already from the very beginning, we're kind of struck by a difficult question. What should we choose to be our elementary gates for a quantum circuit? So it's different than the classical case because we're not just dealing with bits, right? Even just for a 1-qubit gate, there are continuously many possibilities for what your 1-qubit gate can be. Okay, so we need some kind of principles in order to narrow down our selection of gates. Okay, so here are some properties that I think are very natural. We want a finite gate set. We want to generalize classical, reversible, and randomized circuits. Okay, so we want a quantum circuit to be at least as powerful as randomized circuits. And we want some sense of universality, right? We want that any quantum operation, any unitary, can be approximated by a large enough circuit with our finite gate set. Okay? So we're going to be strongly motivated from our classical randomized circuits that we just talked about. Okay, so we know that we want to be able to simulate those kind of circuits. Okay, so in order to do that, it's very natural to include the TOEFL gate. Okay, so what's the action of the TOEFL gate? Well, on basis states, when A, B, and C are just 0 or 1, it has the exact same action as in the classical case. And then we just define its action on any state by linearity. Okay. Okay, so that kind of handles simulating the Toffoli gate, of classical circuits. But we also want to be able to simulate this coin toss gate, right? So what gate can we throw in to also simulate a coin toss gate? Well, a very natural option here is the Hadamard gate, right? So we know that Hadamard gate sends 0 to the superposition of 0 and 1, 0 plus 1. So that means that if we start out with 0, we apply Hadamard, and then we measure, then we're going to get 0 with probability half and 1 with probability half. Okay, so that very naturally simulates a coin toss. Okay. So one drawback to this is that it requires measurement, right? So again, if we want to generate all our randomness at the beginning of the circuit, then we'd have to do all these measurements at the beginning of the circuit. And it's kind of a nicer model to only do measurements at the end of the circuit, at the end of the computation. Okay, so it turns out that you can always defer all measurements to the end of the circuit. So any circuit with measurements in the middle, you can simulate by a circuit where all measurements are deferred to the end. Okay, and on the problem set, you'll prove a part of that. You'll show how to simulate randomized circuits even when you defer all measurements to the end. Okay, so kind of the amazing thing here is that just with these two gates, right, a Hadamard gate and a Toffoli gate, which we came up with very naturally in trying to simulate classical randomized circuits, they can actually, we're already done. These two gates can already efficiently approximate a quantum circuit on any other gate set. Okay, so what do we mean any other gate set? Well, we mean, for a gate where you take any unitary you want on a small number of qubits, say like less than 4 qubits. Okay, and what do we mean by efficiently? Well, we mean that if you have a circuit with some other gate set that acts on n qubits and has m gates, well, there's a circuit that just uses Hadamards and Toffoli's and approximates it up to error epsilon with the same number of gates times a polylog factor. Okay, polylog and nm and 1 over epsilon. Okay, so this is a pretty efficient simulation. Okay, so this result about Hadamards and Toffoli's was originally shown by Xi, and there's also a nice little note by Aharonov with a very simple proof of this result. Okay, there's one more thing that I haven't really defined for you, and that's this notion of approximation here. So kind of a more relaxed notion of approximation is used here than what you might be familiar with. So, the usual notion of approximating a circuit, if you have a circuit U on n qubits and you want to approximate that circuit by a circuit U tilde also on n qubits, then a usual notion of approximation is that the operator norm or the spectral norm of the difference is at most epsilon. Okay, so that's not going to work in this case, because when we're using Hadamard and Toffoli's, then we're actually going to need to use extra ancilla wires in order to approximate our circuit U. Okay, so the notion of approximation that's used here is that circuit U is epsilon approximated by circuit U tilde if there is an ancilla state psi such that for every unit vector phi, if I act U tilde on phi tensor psi, so basically my my circuit U tilde is allowed this extra ancilla state psi, and I look at the difference with just the circuit U acting on phi and then tensored with psi oh, I'm sorry, that's a typo there. It should be psi. So if I look at the L2 norm L2 norm of this difference, that's at most epsilon. Okay, so that's the notion of approximation that is used in this theorem. Okay, so I like this result because it shows that there's a very simple gate set that is naturally motivated from the classical case that is universal for quantum circuits. Okay, but in this course, we're not going to translate all our algorithms into just using Hadamard's and Toffoli's. Okay, it kind of suffices for us that we know it can be done. We're not going to only use Hadamard's and Toffoli's in our algorithms. Okay, so let's go ahead and look at some other useful gates. So here are some 1-qubit gates that you're going to run into a lot. The X gate, or which does a NOT on the standard basis vectors. The Z gate, which does a phase flip, so it multiplies the phase of the 1-qubit by -1. Phase shift, which multiplies the phase of the 1-qubit by e to the I phi for some phi. So of particular interest here is the T gate, where phi is pi over 4. So a 2-qubit gate that you're going to see a lot is the controlled NOT gate. So if the bit on the first wire is 1, then it's going to negate the bit on the second wire. And it's known that the gate set with Hadamard T gate and C0 gate is dense in the set of all unitaries. So this is another very simple gate set that is universal for quantum computation. Okay, let's look at an example here with the controlled NOT gates. So what does this circuit do? Okay, so go ahead and try it yourself. You can pause the video and I will go over it now. Okay, so let's just think that we have an arbitrary bit on the first wire and the second wire. Again, it suffices to figure out what the circuit does on computational basis states, because then by linearity we know what it does on any input. Okay, so this is a controlled NOT. So what we're going to have here is A XOR B. And of course this just stays A. Okay, so now what we're going to have here is A XORed A XOR B. Okay, which of course these A XOR A is just 0, so this is just B. Okay, so that's going to be what we have here is just B. And now we do the similar thing happens here. So now we have A XOR B, which is just A. Okay, so we started out with A on the first wire, B on the second wire. We ended up with B on the first wire and A on the second wire. Okay, so this is a swap. We've just done a swap gate, okay, which is you also see written like this. Okay, so here's another example. So go ahead and pause the video and work this out for yourself first. And now I will start to go over it. Okay, so as I said before, I really like to just think about a circuit like this just one step at a time. Okay, so let's really think about what we start out with. So we start out in the state 0, 0. Okay, now I apply a Hadamard to the first register. So now we're in the state 1 over root 2, 0 plus 1, tensored with 0. Okay, so now we do this controlled NOT. Okay, so we have 1 over root 2. So when the first register has 0, then we're not going to do anything. So that's going to be 0, 0. Okay, and when the first register has 1, then we're going to flip the second bit. So then we have 1, 1. Okay, so that's where we are after doing this controlled NOT. And now we do a Z gate on the second register. Okay, so 1 over root 2. So again, when the value in the second register is 0, we're not going to do anything. 0, 0. And then we're going to flip the phase when the second register has a 1. Okay, so we end up with this state here. Okay, so here's an example of a circuit which has created some entanglement. So it's created this Bell state here.